Touzi. Él nació en Túnez y después estudió en Francia y ha hecho una carrera en la parte de matemáticas financieras, ¿no? Entonces, it's a pleasure for me to introduce Dr. Nizar Touzi. He was born in Tunisia, Cartago. Then he received his mathematical education in France. He has a PhD in mathematical finance, and since then he has become a leading figure in the area. Now he is working at the Ecole Polytechnique. He will talk about nonlinear representation, backward stochastic differential equations, and application to the principal agent problem. Help me welcome Dr. Touzi.
Thank you very much. I don't think it's working. Is it working? No. Is it working? Oh, yes. It's okay. Thank you very much. I am very honored to give this talk here in front of this audience, and very glad to share with you the celebration of this 75th anniversary of mathematics in Mexico. Thank you very much, and I will talk about a very long title, Nonlinear Representation, Backward Stochastic Differential Equations. I could have added path-dependent partial differential equations because the three of them are the same, as I will try to convince you. The three words are the same. And at the end, I will show you an application in a problem which is very popular in economics, namely the principal agent problem, which is used in the theory of incentives. Okay, so maybe when I thought about how to give this talk in front of a diverse audience, I thought it's better maybe to start the presentation from the point of view of PDEs. So I will start from the PDEs. I think the transport equation is widely known by mathematicians in any field. So let me start from there. I start from the very simple first order partial differential equation, the transport equation, where you have a time derivative, and the d here is the space derivative. So you have d dimensions in space and 1 dimension in time. And it is well known that for this type of equation, you have an explicit solution, which is obtained by using the so-called characteristics. So let me review this with you, because later on we are going to generalize this. So when you look at this equation, we have been taught in high school that you have to solve this ODE. X dot, this is dx over ds, equals b of s of x. So the b is the function that you find here. And then once you solve this ODE under standard conditions, then the explicit solution can be expressed explicitly in terms of this, the flow, x of t. And the reason behind that is, of course, under regularity conditions, if you evaluate the solution v along the characteristics, then you get exactly one derivative in time in here, and then one derivative in space times x dot, and precisely x dot equals b, and then by the equation, since v is solution of the equation, this is 0. This means that v is constant along the characteristics, and once it is constant along the characteristics, you just integrate between t and capital T, and you get this representation. Very easy. Very easy. And the question is how to go further, and the next step is to go from the deterministic transport equation and to introduce some viscosity, and then we go to the heat equation. Now for the heat equation, now we have the Laplacian appearing here, and the question is how to extend these characteristics. And for those who are not familiar with the Brownian motion, I would like to emphasize that Brownian motion is precisely the tool which extends these characteristics. So if you don't like probability, if you don't like Brownian motion, you should like it now, because this is the method of characteristics. So the idea is to find a similar object as this solution X, which produces, after two derivatives in space, the same order as the time derivative as the space derivative. And for that, we know that Brownian motion does the job, and Brownian motion is random. You have to introduce some randomness to have this order. So now we find exactly the same equation as before. So this, sorry, I should be writing X, the initial condition here. So we have the first part of the equation of deterministic characteristics, and then we add this random term, this random component, which is involving the so-called Brownian motion. And we will see that this is going to mimic exactly what we have done in the first slide. One thing to know is that we have the so-called Ito formula, which is going to tell us how to take the differential of smooth function v evaluated at the characteristics. So the first two terms are the usual terms which appeared in the previous slide. The next term appears because the Brownian motion has quadratic variation which is equal to t. So if you try to prove differential calculus under Brownian motion, then you have to go to the next order in the Taylor expansion, and therefore you get the second order term which appears. And that is exactly the reason why we use the Brownian motion, because now we have this Laplacian which we want. Now the next step is just to replace dx, and if you replace for dx from this equation, and if you collect the ds term and the dw terms, then you see that the equation appears exactly here. So we have exactly the same phenomenon as in the first slide, except that we have now an additional term which is the green term. So the price to pay is to live with this new term which is a random term. But it's not so bad because this random term has mean 0. So from here, if I do exactly as in the previous slide, just integrate between t and capital T, then so now this term is 0. If you integrate between t and capital T, you just get that the solution is equal to the final condition, g of x capital T, minus this extra additional term. So this is exactly an extension of what we have had in the previous slide, except that we have this addition of 0 mean term. So you can either keep it, or if you take expected values, if you take the mean of this equation, then you get again an extension of the previous slide, because now the only difference with the previous slide is that we have this expected value which appears. Okay, so what I want to say is that from these two slides, what I want to say is that this equation says exactly the same thing as the heat equation. It's exactly the same thing. Now, by expressing it in probabilistic terms, what I want to gain is to get away from this framework and to extend a little bit by introducing some path dependency. So the next slide, I will be talking about the heat equation where we have some path dependence. But now I'm going to extend this formulation. So when there is no path dependence, the two formulations are completely equivalent. Now with path dependence, I'm going to extend this formulation. So path dependence means what? I would like to replace the g of x capital T from here by any function xi of the path of the Brownian motion. Any function xi of the path of Brownian motion, and then what we can prove, this is a result that master students know in the first course of stochastic calculus, any random variable with sufficient regularity, integrability, can be written as some constant plus a stochastic integral with respect to Brownian motion. Again, it's exactly the same thing as here. This is a random variable equals constant plus stochastic integration with respect to Brownian motion. So the z is dv. Z is dv. The z here is the gradient. Is the gradient in the case where there is no path dependency. And the proof of this result is nothing but iterating the proof from the previous slide. For xi, which is of the form g of w capital T, we are exactly in the same context as in the previous slide, and you find the existence of z by Ito calculus, and z is the gradient of the value function. And if xi is a function of a finite number of points in time of the Brownian motion, then what you do is you apply the proof from the previous slide between Tn and Tn minus 1, etc. up to time 1, and at every step you will find z between the time Ti and Ti plus 1. And with that you can cook up this stochastic integral and you conclude by density argument. So what I want to insist on is that this representation is nothing but the heat equation, but in this situation where the final condition is a function of the whole path, is path dependent. Also, you see that we have existence and uniqueness of the pair yz here with this integrability. So if you remember that z was identified to the gradient, at least in the elementary steps here, then you see that what we have as integrability condition here is that y is the value function. So the value function is in L2 in time and space and omega, okay? And also the gradient, z is the gradient. So also the gradient is in L2 time and omega. So we are in the context of W1 Sobolev solutions. So this is exactly the parallel of what we do for the heat equation for PDEs. And exactly as for the heat equation, we can go further and we can add some nonlinearity. So now exactly the similar theorem as before, which was proved by Pardoux and Peng in '92. Let's add some nonlinearity f. So the nonlinearity f is a function of time, omega, so it might be path dependent. It may depend on the path of Brownian motion again. And then it may depend on the value function itself. This is the component y. And it may depend on the gradient. This is the r to the d component z. And as usual in probability, we don't write omega. So f sub s means that there is some omega hidden there. So exactly the same situation as before, except that now we have this nonlinearity, we have this xi which is path dependent, and you can prove by similar methods as for PDEs by taking the Picard iteration and proving that there is a contraction there, that there is a unique solution, and again unique solution in the same space, so L2 space in time and omega for the value function itself, and L2 for the gradient. So this is again W12 type of solution for semilinear heat equation. Semilinear heat equation, I will justify it in the next slide, just in a minute. So again, this is an extension of PDEs, but just with path dependency. So what is the connection with semilinear equations? In here, I have just rewritten this equation in differential forms. So dyt equals minus ft plus zt dw. Okay? Minus ft dt plus zt dw. And final condition y capital T equals xi. So this is what we call backward stochastic differential equation, because you see that we have y on both sides. So it's a stochastic differential equation, and it is backward because instead of setting the initial condition, we are setting the final condition. So in contrast with a deterministic framework where you just invert, reverse time and solve, here we need to find solutions which are adapted to the filtration. Then you cannot just solve it by reversing the time. So these are called backward stochastic differential equations in literature. And in the Markovian case, so if xi is not path dependent, and if f is not path dependent neither, just depends on the current value of the Brownian motion, then in that case we can prove that this yt function is a deterministic function of t and wt. And now we can connect to a PDE via differential calculus. Because now you can differentiate dyt, if v is smooth, this is equal to time derivative dt plus space derivative dwt plus another space derivative, because Brownian motion has quadratic variation which is not zero, which is the 1/2 Laplacian here. And from there you see that now we have two ways to write yt, and these are completely different scales. So we can identify the green terms and the red terms. By identifying the green terms, we find again that the ZT is the gradient, dV, and by identifying the red terms, we get this semi-linear PDEs, where you see that the minus ft of v here, v is y, and dv is the identification of the z here. So again, whatever we have found in this theorem is an extension to the path-dependent case of semi-linear PDEs, and again, in the sense of Sobolev type of solutions. It's not exactly Sobolev solutions in the PDE literature, because in the PDE literature, we would also talk about the integrability of the time derivative, but in this setting, we talk about the integrability of the value function itself and the gradient, no time derivative. But the precise connection was made clear in a paper by Barr and Lucini in '97. So any Sobolev solution in the sense of PDE community is Sobolev solution in this sense, and vice versa. Okay, now my next step is to go to fully nonlinear PDEs, fully nonlinear parabolic PDEs, because so far we have only extended semi-linear ones. For fully nonlinear, it is a little bit more involved, and we have to go to quasi-sure stochastic analysis. Quasi-sure stochastic analysis is stochastic analysis, but not only under one measure. Throughout these slides, I always write P almost surely, so everything is on the support of some probability measure on the path space. And to go to the fully nonlinear case, we have to work simultaneously on many supports, on many singular supports, and this is what we call quasi-sure stochastic analysis. So notations, we work on the path space. So this is the space of continuous paths starting from 0. This is a typical space where the Brownian motion takes values in. And then notations, x is the canonical process. So this is the projection on the coordinates. xt of omega is omega of t. The filtration, which is generated by x, is ft, and this is the filtration. And one important tool to introduce is the quadratic variation process. As we have seen for the Brownian motion, quadratic variation does not vanish. And now we are going to work under various measures, so quadratic variation can take different type of values. So the quadratic variation is defined without exception of any zero measure set by this formula under any semi-martingale measure, because this stochastic integral can be shown to be defined for every t omega whenever x is a semi-martingale, and coincides with the quadratic variation as a limit in probability. For any p, which is a semi-martingale probability measure, semi-martingale probability measure means that the coordinate process x is a semi-martingale under p. So p is a measure on the path space. I will show you some examples of such measures. And also, the other notation is that this quadratic variation process, which is increasing, we can always define this density sigma hat square, which can be possibly equal to plus infinity. So sigma hat square takes different values from one p to the other, but it is defined under different supports. Okay, so examples which are going to be dealt with in this talk are semi-martingale measures p, so that the canonical process has this type of decomposition. Canonical process can be written as a finite variation part with density bt and a local martingale part with quadratic variation which has density sigma t. So any measure p under which the canonical process can be written in this form is a semi-martingale measure, and I will stick to this set of semi-martingale measures. And then I will consider a subset P in this set PW, which is sufficiently rich. I don't want to go through this. Which is, think of P as being sufficiently rich. And I will use the language which comes from potential theory, that P quasi-surely means P almost surely for every P in in this set script P. So of course, if the measures are equivalent, then P almost surely is the same under every measure, but we are going to be playing with singular measures, and therefore this will be relevant. So whenever the sigmas are different, the measures are singular. This we know. And as I will show you, one important tool is to work with this nonlinear expectation. So instead of defining the Sobolev spaces from before, Sobolev spaces were defined by means of one expectation, which for analysts would be an integral under some weight. In our case, we have to work with these norms which are induced by sublinear expectations or capacities, if you want. So we have to take the sup over all measures P in this set P script of the integral with respect to P. Okay? So this is going to play the role of the norms that we had before. Okay, so now the nonlinearity. It turns out that the good extension of the previous case, the previous semilinear case, is to add one more component which I call sigma. So nonlinearity, there is the time component, the path dependency component, the omega, and then the value function itself, the gradient, and we expect to have the Haitian, but in fact I will be taking it with any parameter sigma which is S plus D. It's not going to be the Haitian, but not far from that. Okay, so classical conditions for that. Lipschitz in the pair YZ, not exactly, we need to involve the sigma there. And we need a monotonicity conditions because I will be talking about general infinite horizon fully nonlinear PDEs. And also we need the growth conditions. These are not the best conditions that we can have. One can extend to quadratic in Z, also quadratic in Z here is possible. But let's keep it there. This is the standard type of assumptions where you don't go through too much technicalities. So this is the nonlinearity, and this is what I'm going to call second order backward SDE, and I will show you that it connects to fully nonlinear PDEs. So what is the difference from the backward SDE? Remember, backward SDE from previous slides was this. dyt is ft dt plus z dwt. Now w is going to be in the canonical process. So you see here I have similar terms. dyt equals minus ft dt plus zt. This is, instead of wt I put dxt because I'm going to play with the quadratic variation. And now there is this additional term where k is an increasing process. Now this increasing process is new, and also the new thing is that I want this stochastic differential equation to hold true not only on the support of one measure, but simultaneously on the supports of all the measures in this class P. So it's a stronger condition, it's a stronger requirement. I want the SDE to hold true simultaneously under all these supports. And one more thing, we want this increasing process K to satisfy this minimality condition. So if you want to understand what's going on here, of course, since K is increasing, this expected value is always non-negative. But saying that the infimum is equal to 0 means that you can get as close as you want from 0. Suppose that the inf is attained at some P star. This means that the expected value of this increasing object under P star is 0, which means that K is just flat. There is one measure, if infimum is attained, then there is one measure where this K is flat, which means that on all supports, this is increasing, this term is non-negative, and on some particular support, this term is not there. And this is the connection with the fully nonlinear PDEs, because now let's go back to the case of no path dependency. If there is no path dependency, then the final condition Xi is G of x capital T, as before. The nonlinearity, there should be a sigma also dependence here. The nonlinearity is a function of xt only, not of the path of xt. And then in that case, you can prove that the solution yt is a function of v of t and xt. And you can, again, use differential calculus to derive an equation for this deterministic function v. So on one hand, by Ito formula, dyt is time derivative plus space derivative dxt plus the second order term, because these processes have finite quadratic variations again. And on the other hand, we have this representation, and therefore we can identify the green guys, which tells me again that z equals the gradient, and the red expressions, which gives me a PDE, and the PDE now is of this form: dtv plus 1/2 of plus this Laplacian, if you want, is less than. The less than is because this term is, there's a minus here and the kt is increasing. Less than this function f minus f of t v dv and sigma hat t. Sigma hat t, again, sigma hat square is the density of the quadratic variation. And by using the minimality condition, remember the minimality condition says that this term is 0 under some p star. Or you can get as close as possible to 0 under among these measures p. And then in that case, this is non-positive for any sigma hat, and for some sigma hat it will be equal to 0, or it gets as close as you want to 0. Then you get this sup equal to 0. This is what it means. So this is a kind of AJB equation, if you want. And now it's fully nonlinear, because if you look at this sup now, it becomes nonlinear in the second derivative as well. This is a fully nonlinear PDE, and this is exactly what we wanted to extend. So this is the intuition from this definition of second order backward SDE. As in the Markovian case, it's a natural way to introduce fully nonlinear parabolic PDEs. Okay, now back to our problem. How can we ensure existence of a solution? So again, xi is path dependent, depends on the whole path of x. And in the nonlinearity, there is a dependence on the path of x as well, which is hidden. That's the omega, which we don't write. And under the conditions that I have showed you before, you can prove that there is a unique solution. There is a unique solution to this second order BSDE under these integrability conditions on the final condition and on the nonlinearity. And notice that everywhere the integrability condition is expressed in terms of this nonlinear expectation. So somehow it's a Sobolev space under capacity, if you want. Okay, so this is the main result, and as I told you, you can view this as, to go back to the title of my talk, you can view this as a nonlinear representation of a random variable, because I start from a random variable xi, and I can represent it as a stochastic integral with respect to x with some nonlinearity on the support of a family of measures. So this is what I call a nonlinear representation. You can view it as a second order BSDE if you want, but you can view it also as a PDE depending on the path dependent PDE. So all these notions are the same, in fact. And I would like to conclude by showing you an example where this representation plays a crucial role and simplifies considerably the problem. So the example, it comes from economics, as I said, and it will be a stochastic differential game, which is often used by economists to model the so-called moral hazard. So economists want to organize the society so that we don't count on the morality of the people, because there is always only a small proportion of the people can be moral. So if you want the society to be well organized, the regulation should be set so that people have the incentive to be moral. So this is the question of moral hazard, which is a very old notion in economics, which goes back to Adam Smith, in fact. And the way it is modeled by economists is the following. suppose, so it's the so-called delegation problem. So suppose you have a land and you want to hire someone to take care of your land. And the worker, which is the agent here, devotes an effort, and depending on his effort, the production of the land will have a certain distribution, which I denote XA. So there is an impact of the effort on the production of the land. And of course, by devoting the effort A, the agent has a cost for that effort, because he needs to wake up early, sleep late, doesn't go to see a movie, to work, and that has a cost for him. So if we stop there, then this is a very bad situation for the principal, for the owner of the land, because what you see from this optimization problem is that the only thing which is relevant for the agent is to maximize minus the cost of effort, which means minimize the effort, which means that he's not going to take care of the land. And of course, there is a natural solution which is part of our real life that everybody knows. The principal is not idiot, so the principal pays the agent some salary xi, which is indexed on the production. So by paying a salary xi, which is indexed on the production, suddenly the agent cares in his optimization problem about the output process XA. So he's not only minimizing the effort, but he's minimizing the effort, but at the same time he wants to have a good salary. Okay? So this is the first part of the problem. Given a contract C, which is set by the principal, the agent solves this problem and returns an optimal response A hat of xi. So this is his optimal response to the contract. So if the contract says is very nice for him, he's gonna work like hell, he's not going to sleep, etc. If the contract is bad, he will just return small effort. He say, for this salary, this is how much I'm willing to work. Okay? So this is his optimal response given the contract. Depending on the way you pay him, he's going to devote a certain optimal effort. Now the problem for the principal now is to find what is the best contract that he can offer to the agent, so as to maximize his welfare. So now the principal cares about the production, but takes the optimal response of the agent as given, and pays the salary, accepts to share with the agent part of the profit collected from the production. Okay, so this is a differential game, non-zero sum, stochastic differential game, non-zero sum because we have two interacting agents with different objectives. The principal cares about the land because he's the owner of the land. The agent doesn't care about the land. He's just there to work and to get his salary. So they have different objectives. So they have divergent utilities from the land, and therefore this is called non-zero sum. Stochastic differential game. So we have two optimization problems which interact. And in general, it's difficult. There is one more constraint which is very important here. The principal can only propose contracts so that the agent is above certain reservation level rho. So you can view this constraint as a world without slaves, if you want, because the agent here can say, no, sorry, I don't want to work for this type of contract. This is the meaning of this constraint. Because what you see is that if there is no such a constraint, what the principal can do is make the agent pay, take a negative xi, and if the agent is forced to work even with a negative xi, then he would return an optimal response to a negative xi, and maybe the principal will forget about the production asset and will only care about whatever the agent is going to give him, which is a bad situation. This is the situation of slavery, if you want. So this constraint says that the agent can say, no, thank you, I do not accept this contract. So it's important, otherwise the problem is degenerate. Okay, so this problem is not easy to solve, in fact. Because you see, if you want to, the optimization over Xi appears here as an argument of the optimal response of the agents. So this is a highly nonlinear dependence. And it's even worse because if I continue to write it correctly, I should write here a hat of Xi of x of a hat of Xi of x of a hat of Xi, never-ending type of thing. So if you want to try any standard method of optimization, it's difficult to implement. But it turns out that if we formulate this problem in continuous time, as a stochastic control problem in continuous time, it turns out that this problem is easy to solve, and easy to solve thanks to the representation, nonlinear representation that I showed you before. Okay, so in continuous time, this slide will become much more ugly, but it's essentially the same thing. It's essentially the same thing. So let's turn everything in continuous time. Now the production of the land is measured time by time, in continuous time. And the effort of the agent is the process nu here, the control process nu, which impacts both the drift of this stochastic differential equation and also the diffusion of the stochastic differential equation. And the agent cares about the salary, Xi of x, and about the cost of effort, minus the cost of effort. So again, exactly the same problem as before, and the k is just some discount factor. You can forget about it. Now this is the agent problem, just translated to continuous time. And then you have the principal problem is to choose the best contract. And now the principal problem is exactly the same as before. The principal takes the optimal response of the agent as given and pays the salary and takes advantage of the production of the land. And again, with this no slavery constraint, which says that only those contracts which provide the agent with enough utility are acceptable. Okay, so in fact, we cannot solve this problem in the full generality. We have to take the drift B in the range of the diffusion matrix sigma, and this is very related to regularity. For people who are familiar with PDEs, understand that fully nonlinear PDEs in general don't have good regularity. So under this condition, in fact, we can get some regularity. So the idea to solve this problem is to introduce the so-called Hamiltonian. So this is well known for among those people who are familiar with stochastic control. So if you look at the problem of the agent, forget about the problem of the principal. If you look at this problem, this is a stochastic control problem. It's not in usual form because the Xi is path dependent. The Xi is path dependent. So let's forget that Xi is path dependent and let's do whatever we are used to do. If you have a control problem, you have to write the Hamiltonian. So I'm writing the Hamiltonian as if there was no path dependency. But in fact, it's not important. So the Hamiltonian is the drift times the gradient, 1/2 of diffusion square trace with the second derivative with the Haitian. And then this is the discount factor, comes with the value function. And this is the cost, the integral cost. And everything should be maximized over the control U. This is very standard for people who do control, stochastic control. And then this is definition number 1. Definition number 2, for any scalar, y0, and for any processes z and gamma. So z is valued in Rd, same dimension as x, as the output process, and gamma is valued in the set of symmetric matrices. So this is a trace of gamma times the quadratic variation. And then subtract exactly the Hamiltonian, evaluated at this process of your choice. So you choose y0, you choose z, you choose gamma, and you subtract this h. And this needs to be defined under all measures P, which can be induced by any control. And then the easy result, this result is really easy, is that if you choose any contract of this form, so remember my notation is, if I go back to my notation, I'm calling VA of Xi the agent problem. So Xi is the contract. So if you choose as a contract something of this form, so which means constant payment, this is a fixed salary, plus some proportional salary to the production, and plus something which penalizes the variation of the production. So which says if the production is stable, smooth, or very, very volatile. This is what is said here. Okay? So if you choose this type of contracts, then you know exactly what the agent is going to do. You know exactly what is the optimal response of the agent. His value function is your chosen y0, and his optimal control is the maximizer of this Hamiltonian that I call nu hat of yt zt gamma t. So somehow, if you choose this contract, you know in advance what will be the optimal response of the agent, and this is a big advantage for the principle, of course. If we go back to AJB equations, then you can feel how can we solve a fully nonlinear AJB equation with final condition Xi. This is the PDE corresponding to this problem is very involved. It's a fully nonlinear PDE with some final condition Xi, which is very general. And it's even worse because AJB equation would be in the Markovian case. But here we have, in addition, the difficulty of having path dependence. In fact, notice that I'm choosing the boundary condition of my PDE. Somehow, in the PDE sense, I'm taking this fully nonlinear PDE, and I'm choosing a convenient final condition. So I'm choosing a final condition which is suitable with the PDE, because the Hamiltonian is exactly the Hamiltonian of the AJB equation. So this is why this result is very easy to prove. And the proof is in a few lines. So I think I still have time to show you very quickly the proof. So if we take the objective of the agent is to maximize this expected value. So this is the salary discounted with k, with the discount factor k, minus the cost of effort, again discount with k. So if you look at the performance under any control, given this boundary condition, the Xi, the contract, then I just rewrite whatever the contract, the expression of the contract from the previous slide. So this is the fixed payment, the proportional payment, and the payment depending on the variability, on the volatility. And then the next step is to remember what is dxt. In dxt, there are two components. In dxt, there is the drift component, which is bt dt times the zt from here. And there is the diffusion component, which is sigma dw times dt again. And everything else is the same. And now everything is under expectation. So in principle, this term has mean 0. Okay, you have to prove it. It's not obvious that it has mean 0, but it works. Huh? It's always like that in stochastic control. You have to deal with these local martingales always with the same means. Okay, so this term is not there anymore because it has mean 0. And whatever is left is exactly what is inside the definition of the Hamiltonian. Remember, the definition of the Hamiltonian is this sigma lambda, which is b times z plus 1/2 sigma square traced with gamma minus ky minus c. And this is exactly what we get here. I mean, this is why we define the Hamiltonian like that. So all this expression now has a non-positive sign. Everything is negative by definition of the Hamiltonian. And the only way to make it equal to 0 is to pick up the maximizer from the h. If you take the maximizer, then everything here is 0. And this is why the optimal control is maximizer of the Hamiltonian. So this is exactly the main idea for this proof. And the proof is not difficult. It's a few lines. OK, so from here, what we see is that we have an interesting subset of contracts that I call revealing. Revealing in the sense that if the principal proposes this type of contracts, then he knows exactly what is the reaction of the agent. So the principal may say, okay, I'm going to restrict myself to this type of contracts because I have no surprise. But maybe he's losing something. Maybe he's losing something. This is why I write VP, the principal problem, is greater than the optimization problem if he restricts to these revealing contracts. Maybe he's losing something because maybe he's not considering all possible contracts. Maybe he's missing some interesting contracts. And in fact, what you can prove is that he's not missing any contract. So equality holds there. Equality holds, and whatever is left on the right-hand side is a standard stochastic control. There is no game anymore. We are back to an optimization problem which we can deal with. And any optimal Z star, gamma star, Y star from the right-hand side induces an optimal contract for the game problem. So this is the result. And let me show you how this result relates to the representation. Well, again, we agreed that there is an inequality here because maybe the principal is missing some interesting contracts. So one sufficient condition is if any contract can be written in this form. It's a representation. We have a representation problem because ytz gamma is this expression. So we are asking the question, can we write any xi of x, any path-dependent function of the output process, can we write it in this form? It's a representation problem. It's exactly the problem that we have been working with. But it's not the same form. And the reason why we can solve it is that we don't need to prove that every xi has this representation. We will be done if we can prove some density of these representations. If you can prove any xi can be approximated by this type of contracts in some good sense, so that you can pass to the limit in the problem of the principal, then you're done. And in fact, this is what happens. We can verify this property, and the reason why we can verify this property is the following. So remember this, we want to prove this representation y capital T z gamma, and again this y capital T z gamma has this form, and where the gamma formally stands for the Hessian. Second derivative in a PDEs is something that you usually don't expect in this type of problems, so we want to get rid of it. So to get rid of it, I'm going to collect the terms which contains gamma, this guy and this guy. So the H and the gamma, dxt, I'm going to collect them together and use convex duality to hide the gamma. So you see, this is exactly what I'm doing. I'm taking this 1/2 of sigma squared gamma, and I introduce this sort of convex dual with respect to this parameter sigma, and then I can introduce this H star of this form. And then I introduce KT, which is the difference between H, which is the soup, and anything inside. So it's always non-negative. This KT by definition is non-negative, and it would be equal to 0 if I can pick the maximizer from there. Okay, and now you see that from here I can replace the terms which contain gamma in my representation. These are the two terms here. I can replace them by KT minus H star. So this is exactly what I do. And I rewrite the required representation, xi equals y capital T z gamma, by absorbing the terms which contain gamma and writing instead the term k and the term H star. So it's completely equivalent. I did not add anything here. It's completely equivalent. But now this looks very much like the second order BSDEs from the first part of my talk. It looks very much, except for the increasing process that I called capital KT, which is now forced to be absolutely continuous with respect to Lebesgue. And this is why we need to do an approximation. Now what you do is you start from any random variable xi, has a representation like this, but with an increasing process k, which doesn't have to be absolutely continuous with respect to the bag. You modify this process in order to make it absolutely continuous and pass two limits. And that's the end of the proof. Okay, I will stop here. Thank you very much for your attention.
Are there any questions?
Hi, Nizar. So going back to your main theorem on the existence of the second order BSD, I suppose that it is also related with the solution in the viscosity sense of the fully nonlinear PDE, right? Or not?
No, it's not in the viscosity sense, it's in Sobolev sense. But for fully nonlinear PDE, I don't know what is the analog of this result in the PDE literature. In the semi-linear case, there is the analog is well understood. In the fully nonlinear case, I don't know what is the analog. But it's a Sobolev type of solution because you see the integrability that we have is on the value function and on the gradient. And we want them to be somehow, now this is in LP integrable, but under nonlinear expectation, under capacity. So it's in the spirit of Sobolev solutions, not in the spirit. In viscosity solutions, the Z, we're not even sure whether the gradient exists. So here we have some regularity. Does that answer?
Another question? No more questions? Well, thank you very much.
Thank you.
Questo sì.